Hey, Ollie. Let's go through these linear algebra notes. It's about how linear maps interact with linear independence, bases, and dimension.
Okay, the first question here is, what is the single most fundamental property of a vector space?
Well, a vector space is a set where you can add vectors together and multiply them by scalars, and the results are still in the set. It has to follow certain rules, like the commutative property of addition and the distributive property of scalar multiplication. But the notes don't answer the questions, so let's move on. The next page sets up some conventions. It says we have two vector spaces, V and W, over a field F. There's a linear map, which they call F, that goes from V to W, and we have a set of vectors, V1, V2, VR, that are all in V.
Okay, so f is a function that preserves the vector space structure, right? Like f of u plus v equals f of u plus f of v, and f of cu equals cf of u.
Exactly, you got it. Now for Theorem 1. It states, if f of V1, f of V2, f of VR is linearly independent, then V1, V2, VR is linearly independent.
Wait, why does that make sense? I'm having a hard time visualizing it. Does a linear map always preserve linear independence?
Let's look at the proof. The proof starts by assuming a linear combination of the original vectors equals 0. So a1 v1 plus a2 v2 plus AR VR equals 0.
Then it applies the linear map f to both sides. Because f is a linear map, this gives us a1 f of v1 plus a2 f of v2 plus etc. f of AR f of VR equals 0. Oh, I see where this is going. Since the set fv1 fv2 fvr is linearly independent, the only way that equation can be true is if all the coefficients, the a's, are 0.
That's right. The notes state, but f of v1, f of v2, f of VR is linearly independent. So a1 equals a2 equals AR equals 0. This means that v1, v2, VR is linearly independent.
Ah, yeah, that makes more sense. So if the transformed vectors are independent, the original vectors must also be independent. But does the reverse hold? If the original vectors are independent, are the transformed ones also independent?
Good question. Theorem 2 addresses that. It says the converse is true, but only if the linear map F is injective. So if F is injective and V1, V2, VR is linearly independent, then F of V1, F of V2, F of VR is also linearly independent.
Why does it have to be injective?
Let's look at the proof. The proof starts by assuming a linear combination of the transformed vectors equals 0. So a1 f of v1 plus a2 f of v2 AR f of VR equals 0.
Since f is linear, we can write this as f of a1v1 plus a2v2 plus ARVR equals 0. Oh, now I see it. Since f is injective, its kernel is just the 0 vector. So f of x equals 0 only if x is 0. That means the expression inside the parentheses must be 0.
Exactly. The notes state that because f is injective, we have a1v1 plus a2v2 plus ARVR equals 0. Then, since the original vectors v1, v2, VR are linearly independent, all the coefficients must be 0. This proves that the transformed set is also linearly independent.
This leads to a really important result, Corollary 3. It says that if f is an isomorphism, which means it's both injective and surjective, then v1, v2, VR is a basis of V if and only if f of v1, f of v2, f of VR is a basis of W.
So an isomorphism preserves bases. Why is that a big deal?
It's a huge deal. It also says that if f is an isomorphism, then the dimension of V is equal to the dimension of W. Let's look at the proof. The proof assumes V1, V2, Vn is a basis of V, where n is the dimension of V. Since a basis is linearly independent and f is injective, Theorem 2 tells us that f of v1, f of v2, f of vn is also linearly independent.
Since a basis also generates the entire space, and f is surjective, the set f of v1, f of v2, f of vn generates w.
Okay, so if it's both linearly independent and generates the space, it's a basis of W.
Correct. And because it's a basis, the dimension of w must be n, which is the dimension of v. The proof of the converse is similar. You just use the inverse map, f to the minus 1.
Now for a review of the Rank-Nullity Theorem.
Oh, I remember this. It's about matrices, right?
It says that for an m by n matrix A and its associated linear map FA, the rank of A plus the dimension of the kernel of FA equals n, the number of columns in A. The notes then ask, how can we generalize this to any linear map F from V to W?
That's a good question. How can we?
The notes on this page explain the generalization. First, we need to define the rank of a linear map. It's the dimension of its image, f of v. For a matrix map, f of A, the rank of the matrix A is the same as the rank of the linear map, f of A.
So the theorem for matrices can be written in terms of linear maps as the rank of f of A plus the dimension of its kernel equals the dimension of f of n.
Wait, so the rank of a linear map is just the dimension of its image, and the number of columns from the matrix theorem is just the dimension of the starting vector space.
Exactly. The notes formalize this in Theorem 4. For any linear map F from a finite dimensional vector space V to a finite dimensional vector space W, we have rank F plus dimension of kern of F equals dimension of V.
I see. So it's a generalization of the matrix theorem we already know.
Exactly. Let's walk through the proof. It's a bit long, so let's take it slow. First, they let S be the dimension of the kernel of F and U1, US be a basis for the kernel. Then they let R be the dimension of the image, which is the rank of F, and let W1, WR be a basis for the image f of v. For each basis vector w, I, in the image, we can find a vector v in v such that f of vi is equal to wi. The goal is to show that the combined set b equals u1, us, v1, vr is a basis for v.
And a basis has to be linearly independent and span the space. Let's see how they prove that.
First, we'll show it's linearly independent. We start by setting a linear combination of the vectors in B equal to 0. Then we apply f to both sides. Since the vectors uj are in the kernel, f of uj equals 0. So all of the u terms disappear, and we're left with b1 w1 plus ... plus br wr equals 0.
And since the set W1 through WR is a basis for the image, it's linearly independent, so all the B's must be 0.
Right. The notes say that the original equation simplifies to A1U1 plus ... plus ASUS equals 0. Since the set U1 through US is a basis for the kernel, it's also linearly independent. This means all the A's must be 0. So since all the A's and B's are 0, the set B is linearly independent. Now we need to show that B generates all of V. Let's pick any vector V in V. The image of V, f of V, is in the image space f of V. So we can write f of V as a linear combination of the basis vectors of the image. F of V equals b1 w1 plus ... plus br wr.
Okay. And then what?
We define a new vector, v0, equals v minus b1 v1 plus ... plus br vr. When we apply f to v0, we get f of v0 equals f of v minus b1 f of v1 plus ... plus br f of vr. We know f of vi is equal to wi, so that simplifies to f of v naught equals f of v minus b1 w1 plus ... plus br wr. Since we said that f of v is equal to b1 w1 plus ... plus br wr, this means f of v naught is equal to 0.
So v naught is in the kernel of f. Since u1 through us is a basis for the kernel, we can write v naught as a linear combination of the u's. Since v naught is equal to v minus b1 v1 plus ... plus br vr, we can rearrange it to get v is equal to v naught plus b1 v1 plus ... plus br vr. And when we substitute the expression for v naught, we see that any vector v can be written as a linear combination of the vectors in B.
So the set B generates the space, and we already showed it was linearly independent, so it's a basis for V. And since it has S plus R vectors, the dimension of V is S plus R.
Yep. The notes say that this means dimension of V equals rank F plus dimension of the kernel of F. The proof is complete.
Wow, that's really elegant. It's cool how a theorem that works for matrices also applies to any general linear map.
Now, a few corollaries. Corollary 5 says if F is injective, then the dimension of V is less than or equal to the dimension of W. Why is that? I remember injective means the kernel is just the zero vector.
Right. If F is injective, then the dimension of the kernel is 0. And we know from Theorem 4 that dimension V equals rank of F plus dimension kernel of F. So dimension V equals rank of F. Also, the rank of F is the dimension of the image f of V, and the image is a subspace of W, so its dimension must be less than or equal to the dimension of W.
The next corollary, 6, says if F is surjective, then dimension V is greater than or equal to dimension W. Let me try this one. If F is surjective, that means the image of V, f of V, is all of W, so the dimension of the image is the same as the dimension of W. From Theorem 4, we have dimension V equals rank F plus dimension kernel of F. Since rank F is equal to dimension W, and the dimension of the kernel can't be negative, it must be that dimension V is greater than or equal to dimension W.
Perfect. You've got it. Now, corollary 7. This is a big one. It says that if the dimension of V is equal to the dimension of W, then these three conditions are equivalent. F is injective, F is surjective, and F is bijective.
Wow, so if the dimensions are the same, you only need to prove one of those things and you get the others for free.
Exactly. Let's look at the proof. To prove that injective implies surjective, we start with F being injective, which means the dimension of the kernel is 0. By Theorem 4, dimension V equals rank of F. Since the dimensions of V and W are the same, the dimension of the image, f of V, must also be the same as the dimension of W. The only subspace of W that has the same dimension as W is W itself, so f of V equals W. This means F is surjective.
That's pretty neat. What about the other way? Does surjective imply bijective?
The notes show that if F is surjective, the dimension of the image is equal to the dimension of W. Because we're given that dimension V equals dimension W, we can use Theorem 4 again. We have dimension kernel of F equals dimension V minus rank of F equals dimension W minus dimension W equals 0. A kernel of dimension 0 means the map is injective. So since it's both surjective and injective, it's bijective.
Perfect.
And this all builds up to Theorem 8, which is really the main point of all this. It says that two vector spaces, V and W, are isomorphic if and only if dim V equals dim W.
So if they have the same dimension, they are basically the same space, just with different labels for their vectors?
The notes say exactly that. Let's check the proof. The proof is in two parts. First, if V and W are isomorphic, then by corollary 3, their dimensions are equal. That's the easy direction. The other way is if they have the same dimension, say n, we can pick a basis for V, V1 to Vn, and a basis for W, W1 to Wn. We can then define a linear map F that takes each vi to its corresponding wi. Since the set f of v1 to f of vn is a basis of w, it generates w. Therefore, f is surjective, and since dim v equals dim w by corollary 7, f is also bijective, which means it's an isomorphism, so the two vector spaces are isomorphic.
That's a neat proof, given all the tools we have developed.
The final page summarizes the implications of this. It says that isomorphic vector spaces are indistinguishable and that the only thing that distinguishes different vector spaces is their dimensions.
Whoa, so all n-dimensional vector spaces are basically the same. Like R3 is a specific example of a 3D vector space, but it's not the only one, and any other 3D vector space is isomorphic to it.
That's exactly right. The notes say that if they have the same dimension, vector spaces are the same.
Man, that's a pretty big idea. It really ties everything together. I feel like I finally get what a vector space is all about.
Me too. It's cool how all these concepts, linear independence, bases, dimension, and linear maps all connect to this one central idea about what makes vector spaces the same.
Yeah, thanks for walking through this with me. It was much clearer than just reading it alone.
No problem. I'm glad it helped. We should tackle the next set of notes soon.
For sure. Maybe we can get some coffee first, though. My brain is a little fried.
Sounds like a plan.